Hello. In this video, we are going to continue our study of infinite series by exploring a particular type of series known as a telescoping series. And I'll explore a couple of examples in this video to show how we can use some useful, tricky little algebra techniques to simplify the terms being added together in a series and witness a lot of cancellation, and then this will allow us to figure out what the series actually sums to, what all the terms add up to. And so I wanted to start by saying why we call these things a telescoping series, essentially because the cancellation that we're going to see in the terms reminds us of a collapsible, retractable spyglass, or like a pirate's telescope. So I put a couple examples here. If we click over to this page here, you can see this clip from one of the Pirates of the Caribbean movies. There's Barbossa in the background with his little spyglass, and there's Jack Sparrow whipping out his as well. And you can see in case you haven't seen this type of object before, that's the little telescope, the spyglass that I'm referring to. It's something that you can collapse and expand so it kind of fits in your pocket, or perhaps for sparrows, maybe it's something that you sling over your shoulder. Perhaps a better way to see this is a more modern example. Oops, I don't need a trial, thank you. This is an example. This is not meant to be an ad here. I just want you to see this part right here where the telescope, the spyglass, expands, has a couple of different chambers that are all contained one inside the other, and then it can collapse. And it's this thing we're seeing right now that I think is going to be evoked by the algebraic cancellation we're going to see in some examples coming up. Okay, and here's the example that we're going to use down here. The sum of 1 over n squared plus n, as n ranges from 1 to infinity. So maybe just as a quick little reminder here about what the summation notation means. This stuff in here, this is the term an being defined for me. And that a subscript n equals 1 and the superscript infinity is telling me that n is going to start at 1. By default, we assume that it always increases by 1 at a time along the counting, the whole numbers. The infinity at the top means there's no end, it goes forever. And that red boxed term an means plug n equals 1 into that function, and then 2, and then 3, and that's going to generate all of the terms being added that you see on the right. So for example, when n is 1, I would get 1 over 1 squared plus 1, or 1 over 2. That's the first term in the sum. When n is 2, I get 1 over 2 squared plus 2, or 1 over 6. That's the third term. The second term. And for the third term, I have n equals 3. That's 1 over 3 squared plus 3. That's 9 plus 3. That's 12, and so on, and so on, and so on. And then what we're going to show in the first demonstration in this video is that apparently all of those terms, they add up to 1. The series converges to 1. So I'm saying right now we are going to show that it converges to 1. It should not at all be obvious from what we've seen so far that that is the case. We're going to take a little bit of time to show you how that plays out. So just to give you a little more evidence to convince you of that, and this is also hopefully a good refresher reminder of some topics that have arisen in some prior videos. Remember what it means for a series to converge. We'd be looking at the partial sums, the running totals of adding up a first initial block of a bunch of terms from the series. So the partial sums of a series are the running totals, what we would get from adding up the first 3 terms, the first 5 terms, the first 10 terms, and so on. And in fact, that's exactly what I have written out down here in the example box for this same series that I introduced on the previous slide. The third partial sum here, s sub 3, means what I would get from adding together the first 3 terms of the series. And a half plus a sixth plus a 12th, that all adds up to 3/4. And then for the fifth partial sum, s5, that means adding up the first 5 terms of the series. So that would be a half plus a sixth plus a 12th plus a 20th plus a 30th, and all that adds up to 5/6, or 0.83, and so on. S10 means adding up the first 10 terms of the series, and that all adds up to 10 out of 11, or 0.90909, and so on. And just to give you a hint of where this is going, on the table on the right over here, I have the 20th and the 200th and the 2000th and the 20,000th, all those partial sums. So as I take many, many, many more terms of the series, notice what the running totals, the partial sums, do. They add up to bigger and bigger values, but they're not growing forever. They're getting larger because I keep adding on positive numbers. But those running totals don't grow forever. They seem to be approaching, honestly, it looks like 1. Like I seem to keep gathering 0.999s right after the decimal point. It seems like my partial sums are approaching 1. And this is what it means for the series to converge. The partial sums form a sequence, a running list. That's kind of what I have going on in the table down here. And that sequence seems to be converging to 1. And I just want to be careful right here for the moment and say I'll put this in a question mark right now because it looks like that from the exploration we've done so far, but we haven't officially proven that. We haven't guaranteed that this is the case, but it does seem to be that way. So if you were looking carefully at those partial sums of the few examples that I listed on the left on the last slide, you may have even noticed a pattern. Let me jump back at those for a second. Notice that the third partial sum added up to be 3 over 4. So I have the first 3 terms added together from the series, but the total, that running total, was 3 over 4. And then if I did the fifth partial sum, that added up to 5 over 6. And then when I did the 10th partial sum, that added up to 10 over 11. And you may notice an interesting pattern there, that those fractions always seem to be n, the same subscript under the s, how many terms I've added together. That n divided by 1 bigger, 10 out of 11, 5 out of 6, 3 out of 4. And if you want to verify that, you can look over here and see, for instance, that number 0.95238, that's 20 out of 21. That's another example. This is 2000 divided by 2001, and so on and so on. So there really is that pattern lurking in there. And what we're going to do now, and this is where the telescoping part is going to come into play, is we're going to see that pattern actually coming out from some algebra, not just something that we're guessing and checking from the numbers. And as I note here, it's really okay if you didn't notice that. That's something subtle. As long as it makes sense in retrospect now, that's good. But once we have that formula for the nth partial sum, it will make it much clearer that the limit of the sequence of partial sums is really exactly 1. From this algebraic formula for what the nth partial sum is, we know from our calculus and limit knowledge and function knowledge that as n approaches infinity, n divided by n plus 1 really does approach 1. And it's not like I was noting in the question mark down here. This is not something that we're guessing from a table of numbers. We can actually say with 100% mathematical confidence that this limit really is 1 based on what we know about limits. Okay, so let's look at the third partial sum, which ends up being 3/4. Remember that means the sum of the first 3 terms from the series itself. So another way I could write this is S3 is, and remember I used A to declare what the terms of the sequence, the terms being added in the series, the terms of the series are. I was calling them the A's. So S3 is the sum of the first 3 A's. Now, 1/2 is the function, the number that we got out of the function 1 over n squared plus n when I plugged in n equals 1. Remember that was the an definition. So when I plug in 1, I get 1 out of 2. But it turns out there's an interesting, more useful way to write that, which is 1 minus 1/2. I'll come back to how we would come up with that. But for right now, I just want you to see everything that we're saying as being true. How about 1/6? That's what I would get from plugging in 2 in for n. I would get 1 over 2 squared plus 2. 4 plus 2, I get 1 over 6. Now, it turns out I could also write that as 1/2 minus 1/3. Again, well, I'm going to come back to why in the world I would think to do that, or how I would come up with that. But let's just at least now see why that's true. If I do 1/2 minus 1/3, I would want to do a common denominator to add and subtract those 2 fractions that have different denominators. So in the first one, 1/2, I'm going to convert that into a 6 in the denominator, because that's a common multiple of 2 and 3. So that's like 3/6. And then 1/3, by multiplying by 2 on the top and bottom, that's like 2/6. And so when I subtract them, I get 1/6. And hey, that was exactly what the term a sub 2 is. So again, I'm kind of dancing around this point of, why the heck I would do this, but I hope you agree right now that, yeah, 1/2 minus 1/3 is a genuinely legitimate way of writing the number 1/6. And very similarly, when n is 3, when I look at the third term and I plug in 3 for n, I get 1/12. And another way to write that, apparently, is 1/3 minus 1/4. Well, if I do 1/3 minus 1/4, 1/3 is 4/12. And 1/4 is 3/12. So if I subtract them, I get 1/12. So I guess that's true. All of these things really are 1/2, 1/6, 1/12. Now here's why I would want to do that. Notice all of the nice canceling happening. The minus 1/2 right here, and the plus 1/2 right there. The minus 1/3 right here, and the plus 1/3 right there. And after all of that adding, really all I have left is the +1 from the front and the minus 1/4 from the end. Everything else in the middle gets perfectly canceled out. This is the telescoping action. Here's the lens at one end, and here's the lens at the other end, and there's that long retractable part that I can collapse and expand at will, just like we saw in that YouTube video I was showing you. And that allows me to see where that 3/4 is really coming from. It's 1 minus 1/4, everything else canceled, and that's 3/4. That was the third partial sum, S3, that we talked about on the previous slide. So hopefully now this is a little bit of indication of what I mean by a telescoping series, rewriting the terms being added together in the series to write each of them individually as like a difference of numbers, and then hopefully see a lot of canceling in the middle, a lot of common numbers that are being subtracted in one place and added in the other, so they go away. And that will allow us to really nicely come up with a simple formula. And you can see that it matches up with this n over n plus 1 thing that I've told you we're going to get. And in fact, that's what we're about to do next. Let's see why this pattern happens, not just for the specific number 3, the third partial sum. Let's see why it happens all the time for any possible value of n. So, as it turns out, the crux of this, the key thing that we need to use, is the partial fractions decomposition method. This is something that we talked about when we were learning integration techniques a while back, and we used it to rewrite a rational function as a sum of simpler rational functions, each of which we could integrate. And so one of the first steps we did in that method was to use this decomposition method to undo a common denominator. We're doing that here, but we're not going to do the later steps involving integration and finding antiderivatives. Here, we're just going to use the breaking up a common denominator to take this fraction here, this rational expression, and to split it up into a sum or difference of quote-unquote smaller fractions with smaller denominators, with less factors. So here's what we're going to do. Factor the denominator first. That's what's happened right here when I turn n squared plus n into n times n plus 1. That's me factoring the denominator. And then the partial fractions decomposition, this is something you might want to look back at our notes from that integration techniques unit, but that's this step here. Seeing that I have linear factors, the n and the n plus 1 are both linear, then that means I need a term to account for each one of them, and on the top are constants. A and B are as of yet unknown constant numbers. And so that's what I'm saying here. A and B are constants. They're going to be specific fixed numbers. They can't have the variable n in them. But they're unknown for now. We don't know what they are yet. So the next couple of steps, we're going to do everything in terms of those two unknowns, A and B. We're going to write everything using those letters and then hopefully solve for them soon. So in the next step, that's what I mean by recombining with the common denominator. I have a sum of two fractions right here, and so I could add them together by creating a common denominator. The a term is 1, so I have 1 over n. and the b term is -1, so I have minus 1 over n plus 1. That's another way of writing the original fraction expression, 1 over n squared plus n. So let's go back to thinking about partial sums and adding up running totals of the terms from this infinite series and see what that does for us. We now know this. This is what I just wrote down on the previous slide a second ago. And let's start applying that. So when I look at the fifth partial sum, for the first term, a1, I'm going to plug in n equals 1 in here and here. And you see how I get 1 over 1 minus 1 over 2, or in other words, 1 minus a half. That was the other way of writing the first term of the series, which was 1/2, which is what I would get by plugging in n equals 1 here. And when n equals 2 for the second term, the original series had 1/6 there, because that's what I get by plugging into the an formula, 1 over 2 squared plus 2. But we also see now that I could write that as a half minus a third, what I get by plugging in n equals 2 up there, 1 over 2 minus 1 over 3. And so on and so on, a third minus a fourth minus a fifth, and then a fifth minus a sixth, and then, sorry, I didn't mean to include that final plus sign there. Let's just cross that out. This is the fifth partial sum, so I've added together the first 5 terms. That's what that means. And then here comes the telescoping, the collapsing of the spyglass. There's the minus a half and the plus a half. There's the minus a third and a plus a third. There's minus a fourth plus a fourth. There's minus a fifth plus a fifth. And so after all that, I can see that S5 is 1 minus a sixth, or that's like 6 sixths minus one of them. So that's 5 over 6. And notice that this is following the pattern we keep thinking, that that's n divided by n plus 1. The index number n divided by something that's 1 bigger. And so what I have written down here in the bottom is a way to see that pattern happening and saying this will continue. If I have the nth partial sum for an arbitrary n, I'm not using a specific number like 3 or 5, but rather something that's unspecified, then I would see this is a1 right here, this is a2, I would see a3, dot, 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 dot. This is the n minus 1 term, and then finally this is the nth term where I would stop, because Sn means sum, add together the first n terms from the series. So I'd stop at the nth term from the series. And, okay, to get this one I plugged in n equals 1 into our decomposed fraction. This is n equals 2 in here. This is n equals, and I kept going dot, 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 and this is when I plug in n minus 1 into here. And then this is me plugging in n into here, so I'm just rewriting that thing. And then the canceling happens, minus a half plus a half, minus a third. In the next term there would be a plus a third, then all the other things, plus and minus, they cancel. Right before this term there would have been a minus 1 over n minus 1, and then I have plus one of those. And then I have minus 1 over n plus 1 over n. And so, finally, after all that, there's a 1 up here, and there's a minus 1 over n plus 1 there. And so all of that adds up to, the nth partial sum is going to be 1 minus 1 over n plus 1. Or in other words, n plus 1, n plus 1ths, minus 1 of them. And so in the top, what's n plus 1 minus 1? The ones subtract, cancel out, and I just get n over n plus 1. That's the nth partial sum of this series. Oops. And so let's jump back to what we were supposed to conclude about this series. This adds up to 1 because the nth partial sum turns out to be n over n plus 1, and the limit as n goes to infinity, taking more and more terms, a longer running total, adding up more and more terms for the series, makes the running total, the partial sum, get closer and closer to exactly 1, and that's what it means for the series to sum to 1. It converges to 1. And that would be our conclusion for this example of this telescoping series. Let's do another example. And to start with this one, I might also point out that I would think to do something like this when I see an infinite series like this where the explicit formula that defines the nth term is a rational expression, a rational function of n, essentially a fraction of polynomials in n. And so because I've noticed this, that the explicit formula for the nth term of the series is a rational function of n, I'm going to start employing this telescoping series method. I'm going to apply the partial fractions method to my function that I'm dealing with here. So the first thing I would notice is that I can factor this expression pretty nicely. I get n plus 1 times n plus 3. That will add up to, let's see, n squared plus n plus 3n. So there's the 4n, and 1 times 3 is 3. So good, all of that stuff works out nicely. And so this expression, 1 over n squared plus 4n plus 3, should be able to be written as something over n plus 1 plus something over n plus 3. So when I go to recombine these common denominators, the first fraction here is missing the n plus 3 factor, so I have to multiply that in the top to introduce it. And then the second term is missing the n plus 1 factor, so I have to multiply that by n plus 1 to introduce it. And that would produce the common denominator of n plus 1 times n plus 3 on the bottom. And so in the numerator, we get an plus 3a, and then bn plus b, and all of that's divided by the n squared plus 4n plus 3, that common denominator. And then I'm starting to compare some terms here. So here were the constants. I have a plus 3a and a plus b. Those have to add up to 1 because those are the only number terms that don't have the n, the variable, in it. So from this, and comparing it to the original expression, I'm seeing that 3a plus b has to add up to 1. And then I also see that there is an an plus a bn, and there's no n's in the original. I can think of this, I know we don't usually write it like this, but like plus 0n. So down here that tells me that an plus bn has to add up to 0 n's, or in other words, a plus b has to add up to 0. Now you can start using whatever your favorite method is for solving a system of two equations with two unknowns like this. For this particular one, let's see what I would think to do. In the second row, I see that tells me b is negative a by subtracting that from both sides. And so then I would plug that into the first row. So I get 3a plus b is negative a. That has to add up to 1. So in other words, 2a is 1. And so therefore a has to be 1/2. And then because b has to be negative a, that tells me b is negative 1/2. I could do a quick check on that and make sure that works. If I do a half plus negative half, that does add up to 0. Whew, that's good. And then if I do 3 halves plus a negative half, that adds up to 2 halves, which is 1. Okay, good. Everything all checks out. You can always verify your work like that. And so this is telling me that the original rational function, 1 over n squared plus 4n plus 3, another way to write that is 1/2 all over n plus 1 minus 1/2 all over n plus 3. And so because both of those have 1/2 in them, I would be able to factor out those two common multiples of 1/2. And so when I get to the next slide, I'm really taking advantage of the fact that I rewrote that term, the an expression, as 1/2 over n plus 1, and then minus 1/2 over n plus 3. And then I'm noting that I can factor out that 1/2 from both the top of the first and the second term, kind of pull that out, and that's where that 1/2 in the front of the series is now coming from. And this is something that you may want to do sometimes. There would be nothing incorrect about me leaving the 1/2s in the top of my fractions, but I personally just find it much easier to work with these so-called unit fractions where the top is just a 1. So I'm pulling out that common 1/2 from both of them. And so now let's look at an example of a partial sum just to see what's happening. Let's take an example like s sub 5, let's say. And so that's going to be, well, because of this 1/2 in front of everything, I can just continue to factor out a 1/2 from everything I'm going to do. And then let's plug in n equals 1 into this expression here. When n is 1, I get 1/2 minus 1/4. When n is 2, I get 1/3 minus 1/5. When n is 3, I get 1/4 minus 1/6. When n is 4, I get 1/5 minus 1/7. And then finally, when n is 5, I get 1/6 minus 1/8. And so let's think about where the canceling is going to happen now. I have a minus 1/4 here, and 2 terms later, not in the next one, but in the next one after that, I see a positive 1/4. Those are going to cancel out. And then I see a negative 1/5 here, and 2 terms later I see a positive 1/5, and those disappear. And I have a minus 1/6 here, and 2 terms later there's a positive 1/6. But I do have some things left over. I have that 1/2 and 1/3 appear. They never got canceled out. There was never a negative 1/3 earlier or negative 1/2 earlier to get rid of them. And I also see at the end there's a minus 1/7 and a minus 1/8. And neither of them have anything later to cancel them out. The positive 1/7 isn't coming until the next term when n would have been 6. And the negative 1/8, and the positive 1/8 term isn't going to come until the term after that. So another way to simplify all this stuff is to say S5 is, all right, there's that big 1/2 out in front of everything. And I have the 1/2 and 1/3 added together. And then I have a minus 1/7 and a minus 1/8. And so I have, unlike the previous example, if you'd allow me to jump back for a quick second, the canceling that happened here was always immediate. The minus 1/2 and the plus 1/2, they came in consecutive terms. The minus 1/3 and the plus 1/3, they came in consecutive terms. And the reason that was happening is because the denominators differed by 1. N and n plus 1 always meant that as soon as a positive term happened, the negative version of it was going to occur immediately in the next term, and vice versa. So that means that difference of 1 told me I saw consecutive canceling. But look at the example we're dealing with now. I have an n plus 1 and an n plus 3, and they differ by 2. And so this is going to cause something that I like to think of in my own mind, so I'm going to allow myself to invent the term here. This is delayed canceling. Essentially, each positive number that occurs, I have to wait 2 terms later, each negative term that shows up, like the negative 1/4, I have to wait 2 terms later for the positive version of it to cancel it out. And that's what I'm going to call the delayed canceling. And I can see that happening because these denominating factors differ by 2. And that's also telling me why I have 2 positive terms left over and 2 negative terms left over. Because those 2 negative terms, I didn't see their positive versions to cancel them out. And these positive ones, I never saw their negative versions to cancel them out. So I'm going to have 2 positives and 2 negatives left. And so as you're working on examples at home, pay attention to that difference to see how delayed the canceling is and how many extra terms you'll have left over. So as far as this specific number goes for S5, I could simplify and add and subtract some fractions here. And I'll just do a little bit of arithmetic here. The 1/2 and the 1/3, they share a common denominator of 6 if I want to add them together. So that's 3/6 plus 2/6, so I have 5/6 from that. And then the 1/8 and 1/7, they would have a least common multiple of 56. So I'm going to have minus 8 and 7 more, so it's 15 out of 56 from that. So there I've made a common denominator now out of the 6 and the 56. The least common multiple is 168. So I have 140 minus 45, so that's 95 out of 168. And dividing that by 2 from that 1/2 that I have in front of everything, that's 95 out of 336. That's the fifth partial sum, S5. All right, cool. What has this done for us? Well, to be frank, not a whole lot. I don't want to get too much into the weeds of the arithmetic here, so don't worry about that too much. The real benefit of this is seeing what the canceling is. From this specific example with S5, I want you to notice that the delay of 2 of the canceling. And so I always have a 1/2 plus a third and then minus something at the end. And think about where the 7 and the 8 came from. The 7 and the 8 came from the fact that I stopped at n equals 5, and 3 after that, n plus 3, was 8. But also the one right before that, n equals 4, 3 after that was 7. Those are the 2 terms that I have left. So stopping at n equals 5 caused me to be left over with n plus 3 and n plus 2 in the denominators. And so I'm hoping that you'll agree with the pattern that I would get out of this, which is that the nth term, the nth partial sum of this series, is going to be, so there's the 1/2 in front of everything, and then I'll have a 1/2 minus a 4th. I guess I should write here this formula that I'm using for an, the nth term of the series. And so when I plug in n equals 1, and by the way, I'm going to factor out that 1/2 in front of all of the terms. That's why it's out in front there. When I plug in n equals 1, there's the 2 and the 4. When I plug in n equals 2, I'm going to get a 1/3 minus a 5th. When I plug in n equals 3, I'm going to get a 4th minus a 6th. When I plug in n equals 4, I get a 5th minus a 7th. And I start to see all the canceling happen. There's a minus a 5th plus a 5th. There's a minus a 4th plus a 4th. But all along, I'm going to be left with the plus a 1/2 plus a 1/3. But then everything else is going to cancel out down to a certain point. So I'm going to say plus dot, 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 dot. Remember, I'm supposed to end at n equals this arbitrary, this random number n. So let's write out the last 3 terms. Let's write out here what I would get not only for a sub n, which I'm going to put in here. These are the final 3 terms I would see. So when the index is n minus 2, I'm going to plug that in here where I see n. And I try not to get hung up on the fact that I'm using the n twice here. Imagine plugging in this n minus 2 expression right here in for both n's. And so what I would get is n minus 2 plus 1. So I'm going to have 1 over n minus 1 minus 1 over n plus 1. Remember, that's what I get from making n minus 2 the value of n right here. So I have n minus 2 plus 3. That's where the plus 1 is coming from, minus 2 plus 3. And then when I have this index, everything becomes 1 bigger. So instead of n minus 1, I have n. And instead of n plus 1, I have n plus 2. And then here I have finally n itself. So I'm just going to write exactly what that is, but I can also see how it's every denominator becoming 1 bigger in this term. And let's look at where the canceling is happening. I have a minus 1 over n plus 1 here, and a plus 1 over n plus 1 there. This plus 1 over n is going to be canceled out by a minus 1 over n that happened earlier in the summation. And all things would cancel except for this minus 1 over n plus 2 and this minus 1 over n plus 3. So let me write that all out right here. It appears to be that Sn is 1/2 times in front a 1/2 plus a 1/3. Those are those 2 fixed numbers that I keep having lurking around. and then minus these two things right here that depend on n. And let's plug in n equals 5, a specific number. I would have a half in front times a half plus a third. And then if n were 5, I would have minus a seventh minus an eighth. 5 plus 2 and 5 plus 3. That should sound pretty familiar, because look back what happened when I had n equals 5 and we looked at the fifth partial sum. There's minus a seventh and minus an eighth. What I'm writing now on this new slide is exactly what we saw in this example with n equals 5, but in general, it gives me this formula that depends on n. I can see that the two subtracted fractions left over have n plus 2 and n plus 3 in the denominators. Okay, so from this, Sn being 1/2 of 1/2 plus a third minus 1 over n plus 2 minus 1 over n plus 3, I am now seeking a limit of this expression. What happens as n goes to infinity, as I take a longer and longer running total, as I look at farther down the sequence of partial sums, and I ask, what's the limit of this expression, Sn, as n goes to infinity? Well, I'm going to have 1/2 times something. The 1/2 plus a third, they don't depend on n. They don't care. They're going to stick around. And these two things are going to go away to 0, because as n increases, I have 1 divided by bigger and bigger and bigger denominators. And so both of those things are going to shrink away to 0 as I let n go to infinity. So I'm left with a half times, let's see, a half is 3/6. We've done this addition so many times, I hope you know how this is going to work out. I have 1/2 times 5/6. So this all turns out to be 5 over 2 times 6, or 5/12. This series converges to, it adds up to, exactly 5/12 after all of that work. Here are some practice problems for you to try. Each of these should lead you to something similar, akin to what we've been doing in these examples in this video so far. So spend some time, pause the video right now, work on these, see what you can do, and then in a second I'll flash over to the solution slide at the end for you to check your work. Here you go. The first example that I posed for you is fairly similar to the example we just did together, in the sense that there's a, it's very similar to the first example we did together, in that there's no delayed canceling. The n plus 1 and the n plus 2, they only differ by 1, so you'll see some immediate canceling in consecutive terms. And by looking at the nth partial sum after looking at some specific examples, you think about the general pattern. Turns out that the nth partial sum is 1 minus this fraction. As n goes to infinity, 1 over n plus 2 shrinks away to 0, so the partial sum sequence is converging to 1, so that series adds up to 1. It converges to 1. Now in the second example, you can do some algebra with the partial fractions method. You would have to start by doing long division to get to this, because the numerator is n squared, and the bottom has an n squared in it as well. So because they're tied for their highest power, I would have to do some polynomial division before attempting any partial fractions decomposing. And so you'd find that that rational expression in n, that fraction, can be written as this sum of 3 terms. And so you'll see that, in fact, no terms cancel, because all of those things are plus. They're 1 plus something plus something. So as I look at partial sums, I don't see any canceling happening at all. This is like a telescope that just keeps expanding and expanding forever. There's no collapsing and canceling of terms like we were seeing in the other examples. So this is kind of a quote-unquote trick question, but not too much, because I was actually hoping you would look at this expression here and see that the limit of those terms is 1, not 0. So I didn't even need to bother with any of that algebraic crap. You could have just said, these terms are not going to 0. There is no hope for them to add up to something finite. That's what the divergence test tells us. And then in the third example down there, you would get something like this. Notice that this one has the quote-unquote delayed canceling like we were seeing in the just now example we were working on together, because n-1 and n-3 are off by 2. Please also take note that that series starts at n equals 4, because when n is 3, the denominator is a 0, and for smaller values it could be negative, and so we're avoiding that division by 0 issue and just starting at n equals 4. And you can kind of see that because I have n-3 and n-1, so n equals 4 is the first time when both of those numbers are not 0 and not negative. So you look at all the canceling happening, I see that there are 2 subtracted terms left over from that delayed canceling that I was just referring to. And then take a limit as n goes to infinity, those terms disappear to 0, and so everything adds up to 7.5, 15 halves.